Hey everybody, it's Tom Cherryums with the FujiNet project. And I'm making a video here. I have no idea how long this will be, but it's to basically just dump everything that's in my head and everything that has gone through my head as far as the networking code inside of FujiNet with a plea. Hopefully this is implicit with a plea to try and get more people to help to at least provide some insight and to notice as I'm walking through certain parts of the code, if you have a better way to do something or if you can provide some insight, please try to get in contact with me to try and do this. Now, I'm going to I'm putting this out here after the fact that I've just spent an entire day trying to implement one particular feature, and my brain is somewhat fried and my energy level is somewhat low. So my usual sort of selling an inflection is just not going to sell it here. But hopefully I can try to explain this stuff as clear and concisely as I can. To start, we're actually going to be using the VS Code environment here to walk through the code, starting at the SIO network device itself, ostensibly where the Atari starts talking to the network beyond. This is essentially the end device. And what is the point of the end device? Well, the end device, in and of itself, its purpose is to take the network outside, the network being a connection of all these different hosts of all these different systems off either on the local network or off on the internet, it doesn't matter, talking over TCP IP and with all these different protocols over TCP IP, over 65,535 ports, and to try and provide a clean communication channel that the Atari can understand, both over SIO, to where you can interact with this network device directly over SIO, and over a CIO handler, which makes it easier to use this device, this stack of devices, from inside Atari Basic. Now, this is the network device, and at the end of the day, there are 4 of these network devices that get added into the system here. And so, essentially, when the SIO bus first starts up, we get 4 of these devices given hex device numbers 7.1 through 7.4. And we actually could add some more of them if we wanted to, but I figured that 4 would be enough. If we need 8, then, well, we basically increase this number to 8. It's not that big of a deal. When we first instantiate each of these network devices essentially gets 3 buffers. A receive buffer for data coming in to the Atari from the network outside, a transmit buffer going from the Atari to the network on the outside, and a special buffer which is being used for XIO calls and the like. I don't know if we really need this particular buffer or not, but for the moment, it's here. It's being used to store things like file specs for XIO calls and the like. We'll see what happens. And of course, we make sure that these buffers are set up. They're specifically allocated on the heap. They're cleared. And of course, on the other side of it, when we're done with them, we clear them out and we delete those buffers so that they're gone. Starting off with, we have an open command. And this is rather different than most CIO devices in that because we're having to deal with a lot of different protocols and a lot of different ways that the open can actually happen, we have an explicit open command which its whole purpose is to set things up, to grab in the parameters for the aux1 and aux2 values, apply a translation to aux2 if needed, and set all of that up, then take and do some housekeeping on the protocol if we need to for whatever reason, reset the status buffer, which is implemented a bit later. We go ahead and we parse and instantiate the device spec, where we basically go through and we figure out, coming in, each of the open calls gets a device spec coming in, which gives us in::protocol:, and a path and an optional file name. We parse this into a URL, and at the end of the day, we wind up instantiating this protocol, which ultimately takes and instantiates a class, one of these particular types, passes it back into our protocol object, which we reference all throughout the rest of the network code. And go ahead and finish the open. Finally, once that's all done, we start talking to the protocols. We do an open. If that open fails for whatever reason, we take and try to clean up as best we can, send SIO errors, etc. Now, it's important to note for each of these different commands and types, like open, close, status, etc., each one of these, only the high-level SIO commands actually deal with the SIO bus itself. The protocols themselves have no concept of the SIO bus at all. And in fact, the only assumption that is made at the protocol level is that when we read or write something, we're doing so with a specific number of bytes requested, and we fail if we don't get the number of bytes that are requested for something like a read or a write. This goes hand in hand with the fact that the SIO protocol itself is block-based. You ask for a number of bytes, you get that number of bytes. You send a number of bytes, the other side expects that number of bytes, the other side being the FujiNet, for example. Once everything's done, we go ahead and we start the interrupt timer. This is essentially a rate timer. There's not much going on here, except for the fact that we want to limit the number of times that the interrupt line is pulsed so that the Atari does not become overwhelmed with the interrupt request, because you can actually do this fast enough that the Atari will attempt to service every single time that the proceed interrupt gets pulsed, and will slow down the computer significantly. So we've got a rate timer here that basically is applied, and it's stopped whenever the protocol is actually closed. Finally, we go ahead, and once everything's okay, we're supposed to go ahead and register parsers with the protocol so that they connect in together. But I don't have any of the parsers actually taken and ported over to the network rewrite. The parsers are things like the XML parser and the JSON parser. And those things, since those things have benefits across multiple protocols ostensibly, they're implemented outside of the scope of protocols themselves. They're not limited, for example, to the HTTP protocol, but will be able to be used anywhere else. Close is its complement to open, and not much happening here, but we reset all the status bits, clean everything up as best we can, If we don't have anything open and we're called closed for some reason or another, maybe we accidentally hit the reset somewhere, we just say, okay, we're done, we're complete, we're done. Otherwise, we call, if we do have an instantiated protocol, we call its close method, we complete, we delete the protocol, which calls its destructor, cleans everything up, etc. Finally, we have the read and write commands, which ostensibly get the number of bytes that need to happen for a particular read. And we go ahead and try to, if for some reason we weren't able to allocate the buffers for the strings for these buffers, whatever, then we take and send back an error, bam. Otherwise, if we don't have a protocol, then we're not connected. We send back an error there. Otherwise, we do what's called a read channel. Now, I did this specifically to handle the idea of the parsers. For example, we have whether the protocol, we have the ability to change the behavior of these I/O channels, and we have the ability to change this at multiple layers. We can change it at a global layer for things like turning on or off JSON parsing or XML parsing, or switching between protocols, or switching back to normal protocol behavior. And we have it at the protocol level for doing things like changing whether or not a read means I want to read the content, or I want to read the headers that were sent back, or etc., or write, etc. So we have this ability to take and send commands, SIO commands, to change the behavior of these, to change the behavior of the I/O channel on multiple layers at multiple points. So there are potentially multiple intersecting states that have to be dealt with. And this may be a big point of where bugs can come from in the first place. Of course it's going to be. Conversely, we have SIO write. And SIO write is kind of an interesting one because what we're actually doing is we're getting the data from the Atari, grabbing it in, and then once we grab it in, we go ahead and shove it into our transmit buffer. And because SIO to peripheral only deals with raw data, we have to do this in terms of a raw buffer and not with the string itself. And then take and push it into the casted transmit buffer here. We go ahead and free the result. Finally, we do the channel write itself, which again, we have protocol and things like JSON. For example, if we take and do a write while JSON is enabled, perhaps we're looking for for a query that we want to be able to send and to get back, versus protocol actions like dealing with the HTTP protocol directly or dealing with the FTP protocol directly, etc. Again, multiple layers here. So we have the write and write channel. Finally, we have SIO status. And SIO status, again, has multiple layers depending on whether or not a protocol is instantiated or not. And if we have the ability to do, for local status, if no protocol is instantiated, you can do an XIO3, for example. Or is it, I can't remember exactly, it's 13, I think, that's the status. You have the ability to pass in different aux2 values, to get different things like getting the current IP address, net mask, gateway, DNS, etc., and filling those things out directly as the return values of our status buffer. Otherwise, we have a status channel, in which case we ask the protocol for its status, it returns back a network status object here. And this is as good as a time of any to go ahead and go into the network status object. It's not much, but it's a simple struct which will help split things up nicely. And if we go into network status, we can see it. It's corresponding of 4 bytes, of course. We have a method to take and reset and clear it if we want to. And we have a maximum of 65,535 bytes that we can have waiting in the buffer, 2 bytes, used to encode that. We have this connected byte, which is currently used to indicate whether or not the protocol is currently connected to an endpoint or not. And then we finally have this ability to take and return back an explicit error code, which can be interpreted. And the reason for this is quite simple. It's because SIO is very limited in the error codes that it can return. To give you an example, when you do an SIO call, the most that you will be able to return back will be something like an error 138 if the device times out. An error 139 would indicate that a non-acknowledgement was returned from the FujiNet. There are errors 140, 143, and others which are indicative of what are called framing errors, which are generated by the operating system whenever a serial transmission is garbled. And finally, if an SIO error command is sent, then an error 144 is sent. And in the case of an error 144, we use that opportunity to say, well, okay, if an error 144 happens, then the CIO handler, for example, will immediately do a status and grab this byte, which is the 4th bit in the status in dvstat, to pass back the error code that we really want to return back to the caller. So this is used everywhere that we want to use a status object. It's used by the protocols, and it's used inside the network stack here by itself. So we go ahead and if we can, we do the protocol status, it fills it in, and then we go ahead and fill in the appropriate status bytes. I'm doing this here for readability. I could just to go ahead and collapse this down, but just for the sake of trying to understand what goes into each byte here, we have the number of bytes waiting, we have whether or not the connected flag is set, and of course the error. We send it back, but we go ahead and do a number of debug printf statements which give us, for example, whether or not if the status channel happens, how many bytes are waiting, if an error has occurred, etc. And we send back the serialized status. Now, other things at this point, we have the basics here. So you have open, close, read, write, and you have status. And that leaves every other command. The giant miscellaneous drawer itself, the special. And the way special is handled is in itself very special and very unique in comparison to other Atari device drivers, precisely because of the existence of protocols themselves. I had to come up with a way of specifying, for example, whether a protocol had special commands that it wanted to be able to implement, and to specify at the very least the payload direction for each of those special commands. If I didn't do this, the CIO handler would have to have every single possible command for every single possible protocol encoded in a table inside of the handler, which would be extremely wasteful. So what I decided to do instead was to implement a special command, which is command number 255, so that whenever an inquiry happens, we go ahead and do the inquiry, and we ask, what type of command is it? And built based on the commands, at the very least, what dstat-s should be. Maybe this should be more, but at the very least, right now, it's able to take and specify the data direction. The reason I say it should probably be more is because there are certain situations, such as passing back buffers for read directions for things like getting the current directory, where we might want to take and add on additional parameters to pass back, where this could be helpful. So whenever a command happens that is not immediately specified, the end handler does a special command, ff, which immediately kicks into action whether or not, if a protocol has a special command, which is the inquiry command, which is specified by essentially the aux1 of the ff command. It asks whether or not a special inquiry happens here, and if it's still ff for some reason, then we have a list of local commands or global commands that were, commands that would be ostensibly used across multiple protocols and their potential data direction dstat-s register sets here. And these include things like delete file, rename file, protect, unprotect, change directory, make directory, etc. And we go ahead and set them here. And there are some special ones here for things like setting the interrupt rate or setting translation, which translation we'll get into as we start digging into the protocols themselves. Special commands for handling JSON, parse, JSON query, etc. And then once we get into this point, we figure out, okay, then we need to go into one of these commands here. If it's a local command here, bam, then we go ahead and do it. We do the command, send back the complete, send back the error, what happens. Otherwise, we call the protocol with our command frame here. Send back the complete, send back the error. At no point during the special commands here does the protocol actually do any SIO interaction at all, but tries to perform the requested operation, sending back a true and false, and we do a complete or error based on whether or not that completes successfully or not. Same thing for commands 40 and 80. And you can see some of the special ones for 80. And I have to digress here for a moment. Kind of important, because if you're familiar with the XIO command, and if you've noticed with the XIO command itself can only meaningfully handle commands that either have no payload at all, 0, or commands that send a payload to the device, that's an 80. They don't handle commands, then that's because the only sort of buffer parameter that is sent, as far as an XIO is concerned, is the device specification that's at the end of an XIO command. Anything else would literally require you to literally handcraft a CIO request yourself. And in some cases, such as getting the current directory, you have to do that. But we have our global commands right here. We set them up with the special buffer that we've set up. And finally, we look at the spine of this whole thing, which is just like any other device that's inside of FujiNet itself, to process. At the end of the day, we're only processing a handful of SIO commands, the most basic atomic commands. And I must reiterate, this is the point of the end device itself, to take the vast amount of complexity that exists in the network beyond and to boil it down into a simple set of atoms here. Open, close, read, write, status, special. And if it helps, really, too, you can think of special like IOCTL in Unix. The two are practically equivalent. The other aspect of the network device itself that is absolutely important, that none of the other devices in FujiNet currently use, is the interrupt facility. And the interrupt facility basically deals with knowing whether or not, and this is actually called a bit further up, this is called an SIOCPP itself, to poll the interrupts using a timer that we specify up above, further up in the code, to poll for status if we can get it, and if a certain set of conditions here, if we've got data waiting, or if the connected flag somehow set to 0, then we go ahead and assert the interrupt. We go ahead and keep these values for later. You'll see why in a moment. If we go here to go to definition for assert interrupt, it's pretty simple. It's just a toggle, more or less, where we assert the proceed pin, which is pin 22 on our hardware. And if interrupt proceed is true, then we pull it high, otherwise we pull it low. Excuse me. And interrupt proceed itself is actually defined and used pretty much in the timer. And you can see that each time that the timer is called, the timer that we set up during open, we basically flip this bit. And we do so inside of a critical section to make sure that we don't have any particular deadlocks or race conditions. So that's in essence, that's the network, that's the SIO interface to the network. So you've seen references to what protocols are. And what are protocols? Well, protocols essentially are translation classes. And they're defined in a separate library. Where network CPP was an SIO device itself, if we actually take and fold things up a little bit and go here to another library called Network Protocol, we can start to see the network protocols themselves and how they fan out. And a bit of the possibly insane ideas that I was pushing through while I was trying to design this thing. I will admit that I was designing this stuff rather feverishly, and it may be completely wrong. And if it is, please just stop me and try to tell me and explain to me what I'm doing wrong. Protocol itself, there's not much going on here. We have our 3 buffers that are passed in from our network device, and now you see why I'm using pointers to those strings, as well as the opened URL. We have a constructor, a destructor, a couple of bits of state here, including translation mode, and the different atomic bits and pieces that the protocol is expected to implement. Open, close, read, write, status, special inquiry, and the special commands, which mirror those in network CPP, including those that need to operate entirely on their own, the idempotent commands. We also have a special little function that I've defined at the base class level called error number to error, whose whole purpose in life is to serve as a table, as a mapping, so that given an error number from the low-level portions of the protocol that actually do things, we map those to Atari error codes. And those ultimately get passed back in the status automatically by the protocol. We also have some interesting functions here for translating both the receive and the transmit buffers, which we'll go into right now. We set things up in the network protocol to match the receive, transmit special buffers, get all the buffers set up, do the housekeeping that we need to do, clear everything out as we need to, and ostensibly, the base class here for open, for example, only deals with passing in the auxiliary parameters passed in at open, as well as masking off the translation mode, which currently only uses the bottom 2 bits of aux2. Close, conversely, just deals with clearing everything out. Now, read ostensibly is called by the subclass is ostensibly called by subclasses first, which ultimately call back to this base class. And the reason that they call back to this base class is ostensibly for translate receive buffer. Translate receive buffer's entire reason for existence is to deal with the hairy problem of translating line endings. For the sake of demonstration, we essentially have to deal with other than no translation at all, which is ostensibly used for Atari to Atari communication. We have to deal with translating for machines that use just the carriage return as their line endings. Those are basically Macintoshes. Those that use line feed only as their method of line endings. And those are Unix machines and, well, newer Macintoshes, ironically. And those that use both a carriage return and line feed as their line endings. Now, in all 3 cases, we are actually translating all of these 3 types of line endings into an ASCII end-of-line character, hexadecimal 9B, or 155 decimal. And in this case, the eagle-eyed among you will see that in the case of this third possibility here, that actually requires us to remove a byte in each case that one of these line endings is found in the buffer. And this is actually one of the big reasons why I'm using strings here for the buffer here, because when combined with C++ algorithm here, actually makes it considerably easier to take and remove this extra byte so that we can translate them all into a ASCII end of lines. So we basically replace common characters, change the character return here to a ASCII EOL, and if we're doing CRLF, then we look for instances of line feeds that still are around we remove them from the buffer. And thus, when we're done, we have the corrected receive buffer here. Conversely, for translate transmit buffer, we also have this going back the opposite direction. And going through, after we've done the appropriate end-of-line transformations, if it's CRLF, then we change the 9Bs into CRLF. And we return, in this case, we return the new transmit buffer length so that the length can be adjusted by network CPP so that everything is copacetic. And in this case, too, we have the receive buffer length that also gets corrected by network CPP so that everything is actually correct when we take and send it back to the Atari, when we do the status calls to get the length of how many bytes are actually waiting. All of this is handled at the topmost level of the protocol. We don't have to handle it in any of the other protocols. So that's just there. We deal with that. Furthermore, protocol CPP gives us a basic implementation of error number to error, which gives us a few common global error numbers, which of course this is the global error number sort of function that is set, and it's kind of a macro within a function, depending on how it's implemented on your C compiler. The network stacks will take and set this particular variable, and we can use it to present some meaningful error numbers back to the user. And if we don't have one for whatever reason, if it's uncaught for whatever reason, we can simply return 144. We're done. And that's protocol CPP in and of itself. Now, building on protocol is FS. And FS exists as a file system abstraction. And this particularly deals with protocols that are file systems. Things like FTP, TNFS, and in certain cases, when you want to treat HTTP as a file endpoint. So you're pulling a file off of a web server or you're putting a file to a web server. This abstraction is useful. So we have much the same thing, read, write, status inquiry, etc. And once we go past this point, we have indications of whether or not we are opening a file or a directory, because we want to be able to differentiate, say, if you're opening with aux1 equals 4 versus aux1 equals 6. We have the open modes, which are derived from that, the directory of the currently open file, file name, and just various housekeeping bits to handle file system-like functions. And from that particular point, we start to go into some of the hairier bits of protocol management, particularly when we're doing an open, for example. Since we're passed in both the URL and the command frame, we can basically go ahead, call the base class for this to do any housekeeping that we want to do up here at this level, just in case. We go ahead and we call update dir file name, which basically just takes and splits out the file name and the directory automatically. And if we need to deal with wildcard transformations from different operating systems, then we do that at this point. But we go ahead and then we do any mounting that needs to occur. And this, for example, TNFS needs to mount a particular server before you can use it. For FTP, this is equivalent to logging into the FTP server, and so on. Some certain other protocols don't need it, so this could ostensibly be empty. Finally, based on whether or not aux1 is either 6 or 7, one of these DOSes actually does some special stuff here, and I basically figure, okay, if bit 2, I should just say and 2, if bit 2 is set, then we open directory, else we take and call open file. And open file ostensibly takes, and what it tries to do is set the directory and the file name from our opened URL, split that out as it needs to. Then we try to resolve the file name. And this is, arguably, this is absolutely insane. It's insane, but it's necessary. Because we need to ostensibly take and deal with situations where we can type out the entire file name and use the entire file name. BASIC is a good example of this. It has no problem parsing device specs that are extremely long, up to 128 characters in length. It has no problem with doing that. But certain DOSes and applications can only deal with file names that are 8 characters with a 3-character extension. And so we have to actually take and deal with that. And the best way to deal with that is to go ahead and try to resolve the file names. We do this by ostensibly checking to see if the file exists with the file name that we're trying to use or not. And stat is a function that is actually defined in all of these different subclasses to say, does this file exist or not? And if it does, get me the file size and whether or not it's a directory and whether or not it's locked or not. We go ahead and from that we get directory and a file name. If for some reason this is true, meaning it's an error, it didn't exist, then we try to derive a crunched file name. And this is a utility function that's way off over here in libutils. And if we go to it, we can see it. Libutils, utils CPP. And we try to do some transformation of the file name so that it fits within 8 characters with a 3-character extension. And part of this is to ostensibly take and calculate a checksum of the derived file name and use that as the last 2 characters of the 8 characters of the file name, while using the first 3 characters of the of things after the dot for the extension. So ostensibly this takes and crunches everything down into an 8x3 character file name. If you want to, you can take and dig into this a bit more. This is where it lives. But once we actually get here, we have util crunch. We take and try to resolve it. Okay, great. Then we immediately try to call open dir handle, which is a bit further down in the code, to basically open up the directory. If we can't, we return an error. And we read out each individual directory entry. And we crunch the current entry that's currently being read. And if they match, then we consider the file name resolved. We set the path to the resolved file name, the now long file name that matches, and we do a stat on it. And since it matches here, we assume that the stat matches there too, but the stat will give us essentially all of the bits and pieces of the file name that we need, the file that we need. Again, as a reminder, the name of the file, the size of the file, whether the file is locked, whether the file is a directory. Finally, we close the directory handle and we say, okay, fine, great. We go ahead, say it's resolved to this. Bam. That's the resolve function in a nutshell. So we have this ostensibly happen only in certain cases. Let's say, for example, if aux1 is 4, if aux1 is just the standard open file, then we expect to want to try and take and resolve this file name. Then we take and call open file handle. Now, open file handle is implemented in different ways across these different protocols. For FTP, we call the FTP class to actually take and open the file, for example. For network HTTP, we take and set some house cleaning modes here to be ready so that when we take and do the HTTP transaction, the right thing happens, and so on, and so on. These are implemented by the different subclasses to do what we need to do. Conversely, with directory, the idea with Open Directory here is to try and do as much common logic up on the base class as we possibly can. This includes handling wildcards, translating wildcards consistently, and resolving file names as we need to. And furthermore, if we are, for example, setting aux2 to 128, as is common in DOSes like Sparta DOS and other DOSes, for example, OS A plus version 4 actually sets 128 here as well. Then we want to take and give a nice long entry, which gives the full file name and characters. Otherwise, we take and construct a directory entry that's based on our crunched file name here. We see util crunch before. There's also util entry, which gives us, once you get a crunched file name with a file size, directory, etc., then we take and construct a text string that looks like a DOS2 directory entry and pass it back. This will all make sense soon, I know. We drop a trailer, we're done, bam. And this is the idea here. The base file system class here is just here to implement common elements for all of the different network file systems, mostly housekeeping functions. Close file, close directory hand, close directory, etc. Whether we are reading from a file or we're reading from the directory, etc. And the idea here with the file system, of course, we go ahead, we do the block reads we need to do, we append those things to the received buffers. Since we're dealing with files with known quantities, we take and subtract from the file sizes if we can. Return successes, free the buffers that we need, and so on. Same thing with directories. It's kind of interesting because we need to, because we're needing to basically do all of this translation and stuff. when we open a directory, we're actually having to take and read in the entire directory into a directory buffer, or a directory cache, as you want to call it. And then finally, when we take and do a read from that directory, we're not doing the directory read at that particular point. We're just ostensibly reading from that directory buffer, passing it in and erasing the result once it's been passed into the receive buffer, and calling network protocol read to do any top-level translation that may need to be done. Same thing when we do a write, we go ahead and try to call the parent class translate retransmit buffers to do any line-ending translations before we actually try to take and write out with our protocol subclasses the appropriate file. Status file and status directory. Again, much the same thing here, except when we're doing a status call on a directory, we're getting back the number of bytes that are waiting from the directory buffer versus the number of bytes that were returned from our file stat here. In both cases, we make sure that we try to take and set a network error end of file when we reach 0. There aren't any particular commands that are implemented here at FS, although there potentially probably could be. Instead, what I wound up doing was implementing what were the idempotent commands and calling them from network CPP as need be for the things like rename, delete, lock, unlock, make directory, remove directory, and the like. The only common bit here is the rename, because I wanted to basically have common syntax for the rename function that is old name, comma, new name. And I wanted to take and provide the parsing here for that and not have to implement it in every single subclass. So that's FS in a nutshell. We can actually start to see some of this stuff implemented in some of the other file systems here. But we'll actually take and do a side step here. And in fact, I actually should have gone here first. The simplest protocol that we can think of is the TCP protocol. It's dirt simple. There's not much happening here. We just instantiate ourselves, and as we open, we figure out whether or not we want to be listening for a particular server socket or not, and do the right thing. We go ahead and do open client, for example. We create our TCP client here. We do the connect. And if for whatever reason this fails, then we call error number to error, which is already defined up here in the top level of the protocol here to do a basic error mapping. Some subclasses override this, TCP does not. And any special commands that we actually need to do here are actually implemented here, for example, accepting connections for server connections, etc. Closing client connections. And this is a special case because of how LWIP actually tends to hold on to listening sockets for a very long time. So it was important for us to implement a special command, a special form of close with a lowercase c, to take and disconnect the client while still keeping the listening socket available. But other than that, there's really not much going on, because we do status, we basically fill out, we do the reads, we do the writes, we figure out how many bytes are available, fill out the status objects. When we ask for a certain number of bytes, we pull them in. We read a certain number of bytes in from the clients, from clients, and so on. It's pretty straightforward. And in each case, we go ahead and we call things like network protocol read to translate the data that comes in, pull it into our receive buffer, call our read base class to translate it. Versus here, we take and translate the transmit buffer ahead of time, do the write, and so on. I cannot remember the reason why I did not explicitly call the write base class. There was a reason I didn't do that. Can't remember. Sorry, been long enough. Status, again, we're just mapping out the individual bits from the protocol, from the underlying protocol itself, into things like the status object, into things like the receive, transmit buffers, etc., filling everything out as required to take and implement a needed protocol. This only gets more complex with file systems, but for basic stream-based protocols, we can see right here that there's really not much to it. And ironically, Telnet basically builds on network protocol TCP explicitly and just adds in the necessary telnet processing. Not much else going on here. Boom. There is a very simple test protocol whose whole purpose is basically just to be a dummy protocol. It's a good skeleton to base something off of. So we saw the protocol base class, the FS base class, we saw TCP. UDP is pretty similar, ironically. However, instead of using the FN TCP, it uses FN UDP underlying. And the main thing that happens here is that it is essentially just dealing with basically filling up getting packets in, filling up the receive buffer as it needs to, or sending out the transmit buffer, basically chopping things up into UDP packets. There's no bounds checking that's done with the UDP protocol. So you have to make sure that anything that you send out is basically less than 512 bytes. Otherwise, you're going to get fragmented. Main difference here is that when we do a status, the status is where the packets are actually received and they're passed into the receive buffer, and we go ahead and set the remote IP if we need to, so that our next packet will go back to the person that sent us the last packet. And the interesting thing about UDP is that because UDP is actually connectionless, we always assume that while UDP is instantiated, that you're always connected to somebody. There's no disconnected state. Again, the only The only special command that's actually implemented here is D, so that you can explicitly set a destination host. I have some bits and pieces in here for implementing multicast, but we need to take and do a lot more work to really test this out and make sure that it works well. So now that we know that, we can look at, for example, one of the implementations of Network Protocol FS, which is Network Protocol TNFS. And when I wrote Network Protocol FS, I actually had Network Protocol TNFS in mind. You can see the different subclasses that get implemented, such as Open File Handle, Open Directory Handle, Mount, UMount, the FS error to error, and so on. We'll take and fold these out and bring these back out as we need them. So here we go. Ostensibly, as part of the constructor, we figure out, okay, which commands are actually implemented here. Rename, delete, make directory, remove directory are actually implemented. And we have functions for whether we open up files or whether we open up directories. And whether we open up files, it's pretty simple. We basically just need to map out, since we have access to the aux1 value that gets passed into open. If we're passed in 4, that becomes read. 8 becomes basically a write with delete with extreme prejudice anything that's already there. And 9 is explicitly for append, while 12 ostensibly takes and opens up something that can be opened as read and or write. So we take and set the appropriate mode bit. We currently take and hard code the permissions here. I don't really know how best to handle this. This is essentially a permissions mask that gets passed into TNFSD with default permissions basically set to this, masked against this. Finally, we take and do TNFS open. And in a common pattern that actually happens, once we do the particular error here, we go ahead and immediately take and do what's called FS error to error, which ostensibly provides a table of common TNFS errors that can happen. And we map those from those TNFS errors to Atari error codes. And these actually, this particular network protocol error gets passed up every time that a status actually occurs and gets passed in as the 4th byte of dvstat so that we know what error actually occurred. Do the open and so on. Furthermore, for opening directory handle, we just call our open directory here, bam. And the whole reason for splitting out directory and file name in the FS class above was literally for cases where the underlying protocol explicitly deals not with things as a whole path, but with things as a directory and file name pair. Mounting, much the same way here. We take and do the mount, we fill out all the low-level protocol information, do the call, again, same pattern, FS error to error, bam. Unmount, same thing. FS error you saw there, and we have the read file handle. And at this particular section of the protocol here, it's the responsibility of the protocol to take and do all of the necessary bits that it needs to do to ensure that the read will happen with the requested number of bytes. In this case, because TNFS works over UDP most of the time, and since UDP has a practical limit before it starts fragmenting, we need to take and split up the blocks into the number of blocks that are, against maximum payload. And to take and request each of these blocks individually, to concatenate them together, and to pass them back in to the buffer that's passed in. Now, when we take and do a read of directory entries here, we want to take and pull out all of the relevant information that we know we want to pull out, such as file size, mode, is directory, is locked, etc. Close file handle, much the same thing. Close directory handle, close all the low-level bits and pieces. Write is the complement of read, and the same exact deblocking logic actually applies here too, because the same payload requirements also apply here too for TNFS. Special inquiry, we need to make sure that if we are passed a rename, delete, make directory, or remove directory here, that's Atari to peripheral, bam, okay, no problem. And we have our special 40, etc. Rename. For each of these, we take and do the appropriate TNFS function for rename, delete, etc. The only other thing that happens here too is that we have stat, which is called all over the place, and you'll see references to that all over Protocol FS, especially in places like Resolve, for example, where ostensibly the calls to stat will check and see if the file actually exists or not. And if it is, we take and fill out the bits and pieces that we want to keep track of. Lock and unlock are here, and while there are functions to actually take and do these, the TNFSD currently does not implement them. So they're here for future expansion. TNFS works pretty well. It actually functions exactly as you would expect it to work. Great. FTP is another protocol here that I have somewhat working. I'm having to take and basically work out the state machine because FTP is a line-oriented protocol with certain states and certain things that can happen within those states that need to be mapped out correctly and trapped appropriately. And it's not 100% yet. But in each of these cases, the pattern is exactly the same. You have open file handle, open directory handle, read file handle, etc. And again, you have FS error to error, which takes, in this case, maps out all of the appropriate FTP error codes to their appropriate Atari error, and so on. We go ahead, we try to read the file into the requested buffers, read directory again into the requested buffers, close the directory handles, etc., etc. And in each case right here, again, we have status for file, status for directory. And the various idempotent commands, which I need to actually take and fill in when the FTP bits come farther along. But that's FTP. Now, if you're still awake, now we get into HTTP, and this is where things go off the fucking rails. FTP is a subclass of Network Protocol FS. But why is that the case? Well, it's because of that. It's literally because of that right there. It's so that we can support WebDave mode. And that is if you're connecting to a web server that can support the WebDave verbs like prop find, like make call, etc., then it will work. You will get a directory back when you ask for a directory, and so on. So in this way, it acts like a file system. HTTP isn't just a file system, though. It is, in and of itself, like the end device, a bit of a Swiss Army knife. It is being used and abused as a way to create a sort of generalized endpoint for all sorts of information. And because of that, the current idioms that I have with assumptions with regards to file systems kind of break down. Of course, we have network protocol, HTTP. We have a whole bunch of other stuff that happens in here too. Now we have an HTTP channel mode, and this is where the protocol area, this is where the protocol level of channel modes actually comes into play, because there are multiple channel modes. We have the primary mode, which means to data, which grabs things from the body. We have collect headers, which is used to specify, I want these headers when this request goes out. I want to get these headers back. And get headers, which actually gets the values for those headers that you request, for the keys that you request. And you have set headers for specifying headers that you want to send back to the servers, that is, keys with their values. And you have a mode which is called send post data. And the whole point of this is literally so that you can say, I'm going to change the write mode for a moment, and I'm going to write to the channel, and this is the data that I'm going to take and post back. So we have our HTTP channel modes. And we actually take a look here, we'll see open file handle basically sets up the HTTP modes appropriately. And you can see from the comments here the differences between some of these different modes and why there are different modes. We are basically using aux1 equals 4 for opening plain Jane files. I want to treat whatever the endpoint is you give me, whatever the URL that you give me, I want to treat it as a file that I want to read. I don't want to write to anything. I just want to take and retrieve this with get. There's no headers I want to take and pass through. There's nothing I want to take and push through. And this is absolutely important because, again, at the end of the day, this is mapping cleanly up through the layers, ostensibly to CIO. And if aux1 just has bit 2 set, which is 4, and bit 3 is not set, which is 8, then it means I can only read from this. I can't write to this. So I can't print any headers that I want to be able to retrieve. So this is just for, I want to take and grab something, and I don't want to do anything special with it. For that mode, we actually take and turn the read-write bits on both, which gives us 12. And in this case, it sets the HTTP open mode to get. Finally, in the case of 4, file name resolution is actually attempted. This means that all of the code that you saw for resolve in Network Protocol FS, this gets called. This gets called to take and resolve 8.3 file names to long file names and vice versa. If you set 12, no file name resolve is actually going to happen. Finally, we have essentially write with file name resolve if need be. And this translates out to put. This literally allows you to take and write a file to a web server. And finally, we have 13, which also takes and turns bits 2 and 3 on, but also adds bit 1, which basically says, okay, this is going to be post. And this essentially sets, okay, so post can set headers. It can read to the channel and it can write to the channel. And we want to make sure that we understand that this is for a post request. So being able to take and set post data is also important. So if for whatever reason, if we came back through here and the resolve takes and tries to open a particular file handle and it breaks for whatever reason, and we get something that is an error, HTTP result code of 400 or greater, then an error happened and we need to take and map that out. Again, like since we are basically descending from Network Protocol FS, we have FS error to error. And if we take a look at what that is, I've gone through and mapped out all of the known HTTP error codes to something that the Atari should be able to should deal with. So basically, open file handle just sets things up. It does the little house cleaning. Now, with open dir handle here, since this is with the bit 2 set, so this becomes aux1 becomes 6 instead of 4. Client begin is already called. We have already set up the connection in mount. What we're essentially doing is doing a prop find here, grabbing the result of that prop find, pushing it into, parsing each directory, parsing the buffer that comes back, putting it into our directory buffer, and then we're basically done. At that point, we go ahead and reopen the HTTP client as we need to. And mount is rather interesting because this is where I'm really not 100% sure what to do here. Again, the operation of HTTP is rather schizophrenic. We need to be able to get status information. And we're only going to get status information if file size is greater. Since we're deriving from Network Protocol FS, if file size is greater than 0. And if we're opening directories for some reason, then we go ahead and get rid of all the wildcard crap because we simply don't need it. And we do our client begin. Client begin starts the connection. Everything's good here. If we unmount, we go ahead and delete the client and we're done there. Status. And this is where shit gets weird. Recall that we are constantly polling status. So at the end of the day, status is being called somewhere. It's being called in FS here. Boom. We're calling network protocol. Since we're network protocol status, since we're dealing with a file, we're calling status file here. And therefore, in most cases, if we know the size of the file, then we return the size of the file. If it's greater than 65535, then we return 65535. We return connected if we still have bytes in the buffer to be read, as determined by file size. And then status error, we either return end of file or not, depending on if we need to or not. This works great if the content length is set. This goes to shit the moment that chunked transfer is done. Because at that point, the content size is set to -1, and we have chunked set in the header. We no longer know how many bytes are remaining, and I'm not exactly sure how to work around this. This is one of the problems. Another of the problems is because status is constantly being pulled, I can't go ahead and do this. To ensure that we have some bit of status information that actually makes sense. Because the moment that the HTTP transaction actually happens, we go ahead and do the transaction. We collect all the headers that we have up to this point, and we do the individual verbs themselves. And with this, you actually start to see why there's a separate post command, why there's a separate post mode here, because we have to take and send off our payload as part of our transaction. And once this actually happens, all bets are off. That's it. Boom. We are done. We can't go back. This breakfast has already been cooked. So it's a bit of an interesting issue because things start to go horribly wrong. Because at this point, if we start to do anything that deviates out of the normal of just reading a file back, you'll start here. Let me just open a monitor and you'll see what happens. Am I already on? Well, let's see. Let me see. Oh, I am. Okay. So here we go. We're going to do, as part of our little thing here, 2 different calls. And we're going to look at this thing here. I am not sure how I'm going to pull this off. Let me see if I can reactivate the display here. Okay, it's now active. And I'm going to take this guy and we're just going to kind of put it over here somewhere. Okay. Maybe that. Okay. Tale of 2 different calls. First of all, when you see the close, you see that close actually happening. Again, because we have to talk to the protocol somehow, and we have to do it over SIO. If I take, for example, and do a standard read, Let's take and do that, for example. What has actually happened here, because we're doing a 4 here, it went ahead and had to resolve the file name. So it had to do all of the things it needed to do to perform the HTTP operation, get all of that up and running, so that by the time I take and read from it, and actually, sorry, let me close that out because I did that slightly incorrectly. I need to set the line ending appropriately. So we have dim, and if we start inputting from that, we can actually see, oh, I think I've actually broken this now. Yes, okay. So I've just straight up broken this. Oopsie. Never mind. Let me just see if it'll still load files. Okay, well that's working. So straight binary is working fine. You can see that's okay. Boom. And you can see that it basically it resolved the file name and then proceeded to take and stream that file all the way down. Okay. Things start to go horribly wrong, however, when we start to do, say, a post request, or just say a get request to an endpoint that I have written, running in Go. Over on TMA2, port number 8000 here. Now, you can see what's happened here. Take a look. It has, because of the status command, it's performed a status because of the interrupt, because it's thinking, oh, well, there's something that needs to happen. We need to see if there are any bytes that we need to grab. So it's already done the HTTP request. I can't add anything on top of it. And so any sort of command that I would use to set the header mode to, for example, add additional headers, I can't really do because the transaction has already happened. And I'm not exactly sure how to take and adequately sequence all of these events so that if we need to do things before the transaction happens, they can happen. And it's not as simple as turning off the interrupts, because the CIO handler and other programs rely entirely on interrupts on those interrupts to function. If we turn everything off, everything will basically go to a standstill. So it's really kind of a mess. And I'm not exactly sure how to handle it. And I've gone on for far too long here. I've just been rambling incessantly, deep diving into this code as it exists right now. I have no idea if anybody's going to watch this or try to dig through it, but I figured I would document it anyway. And seeing as my fingers have been typing nonstop, I felt it was more prudent for me to just make a video and try to talk for an hour and a half instead. So, yeah, that's where things are at right now. Just trying to take and work through this stuff. some of the difficulties that I'm running into, some of the architectural changes that challenges I'm coming up against. And this is now the fifth time that I've rewritten the end device, and there may be room for a sixth. Who knows? I could really use some help. Until next time, guys. Have fun.